Okay. Now, maybe a couple of examples will help us consolidate these concepts in a very simple manner. Okay. Example number 1. Supposing I have the sequence x of n is equal to a power n u of n. Okay. Now, remember when we were doing the discrete time Fourier transform, what was the condition for the discrete time Fourier transform to exist? A has to be less than 1, mod A has to be less than 1. So, for DTFT uniform convergence, mod A must be less than 1. Okay. Now, let us see what it translates into for the Z transform. Okay, let us write down the expression for Z transform. The Z transform says summation n equal to 0 through infinity a power n z power minus n. Geometric series, I can write the summation as 1 over 1 minus a z inverse, provided the common ratio a times z inverse modulus of that is less than 1. Okay. And this then, if you simplify, says mod z is greater than modulus of a. Very, very interesting. Now, supposing we take the value a equal to 1/2. Okay. Please sketch the region of convergence. The region of convergence, a circle with radius 1/2, r equal to 1/2. Is there a pole of this, does this system have a pole? Yes, it has got a pole. Maybe we can do the pole 0 expression right here. So, x of z is equal to z divided by z minus a, if you simplify this. Okay. So, what is the expression for, where are the zeros? The zeros are at z equal to 0. That is when it will, where is the pole? There is a pole at z equal to a. If you take z equal to a, then it will explode. Okay. So, in this particular case, we have taken a equal to 1/2. So, there is a pole at, pole is always marked with an x sign, that is a equal to 1/2. Okay. Now, that is the radius of the circle that is passing through radius equal to 1/2. Now, the region of convergence is everywhere outside of the circle with radius r equal to 1/2. It does not touch r equal to 1/2, because r equal to 1/2 has got a pole. So, you cannot have a pole in the region of convergence. Okay. Very interesting. Now, in this case, is the discrete time Fourier transform, does it exist? Where is the unit circle? The unit circle is the blue line, that is z equal to 1 or r equal to 1. Okay. So, this is the r equal to 1 or unit circle. It is in the region of convergence, correct? And therefore, DTFT exists for this case, which we already knew, but it is consistent. DTFT will exist. Okay. Now, interesting extension. Take a equal to 3. Okay. Same condition. You will get ROC mod z greater than 3. Okay. What does that look like? So, sketch it. So, this is r equal to 3. So, there is a pole at r equal to 3, and the region of convergence is everywhere outside of that pole, mod z greater than r equal to 3, everywhere outside. Okay. So, all right. So, and again maybe you can draw it with a different color. This is the pole. ROC cannot include the pole, so it can go outside. Now, the key question is why did we not take inside the circle? And the condition turned out to be that, when we applied the condition for the existence of the Z transform and the convergence of the geometric series, this is what we got, and we'll come in a minute to see. Now, where is the unit circle here? Unit circle is here. This is r equal to 1, this is r equal to 3. So, in this case, the Z transform exists. Z transform exists. So, we can apply all of the transform techniques that we have. The region of convergence, ROC, is mod Z greater than 3. But clearly, that will be a sequence that will not converge for the discrete time Fourier transform. So, discrete time Fourier transform does not exist. Does not exist. Okay. So, now you can see why the study of Z transform is very important, because when the discrete time Fourier transform does not exist, we can still get a transform domain representation and use all of the transform domain tools that are available to us. Why did we spend so much time studying the discrete time Fourier transform? Because that is the powerful transform. However, the Z transform is a generalization. When the Z transform, the discrete time Fourier transform does not exist, we can still get a meaningful representation in terms of the Z transform. Okay, so very important result, and I hope you are able to appreciate what are the benefits of working and studying the Z transform. Let us take one more very simple example. The same sequence, x of n is equal to a power n u of n, we take the value a equal to 1. So, that means you get the unit step sequence u of n. Okay. And we know that we have just now in the last session, we calculated the discrete time Fourier transform, and we said it is a discontinuous function, there will be delta functions and all of that. Now, is it easier to work with the Z transform? Let us look at it. Okay, what is the Z transform? X of Z is summation n equal to 0 through infinity Z power minus n. This is 1 over 1 minus Z inverse. Z inverse must be less than 1, right? That is the condition, that is the geometric series convergence condition. This is the same as saying mod Z is greater than 1. Very simple, right? There is no delta function, none of those things. What is the region of convergence? Region of convergence, this is a case where there is a pole at Z equal to 1. There is a pole at Z equal to 1, because at Z equal to 1, you will see that this transfer function goes to infinity. There is a pole at Z equal to 1. So, the region of convergence is everywhere outside. It should not touch the circle R equal to 1. Everywhere outside is acceptable. Okay, so notice I am drawing it carefully not to touch the circle, because the condition is mod Z strictly greater than 1. It is not greater than or equal to 1, it is strictly greater than 1. So, you can go as close to the circle as you want, but you cannot touch the circle. So, that is the region of convergence of the unit step, the Z transform of the unit step. Okay. And clearly this is a case where unit circle is not included, because unit circle is the one that passes through the. So, DTFT does not converge uniformly, which we knew. Does not converge uniformly because the unit circle is not, so this is r equal to 1. Okay, this is r equal to 1, does not converge uniformly. Okay, I hope you are starting to feel a little more comfortable with the notion of a Z transform, what it can do, what are some of the benefits, why we would use a Z transform instead of the discrete time Fourier transform. Here is a classic example. Unit step is quite, you have to be very careful when you deal with the unit step in the discrete time Fourier transform. With Z transform, not a problem, it is just the region of convergence is mod Z greater than 1. So, therefore, we know how to handle that. Now, there is a very important class of functions for which we will always be looking to compute the Z transform, and I would like to spend a minute to study that. Supposing I gave you a finite length sequence which is given by 1, 2, 5, 7, 0, 1. Okay, and the origin is given as 1. Okay, I would like you to write down the corresponding x of z. Just apply the formula. This will be 1 plus 2 times z inverse plus 5 times z minus 2 plus 7 times z minus 3. There is no z minus 4 because that coefficient is 0, plus z minus 5. Okay. This is a fifth order polynomial. So, finite length sequences will produce a Z transform which is a polynomial of a finite order. So, this is a fifth order polynomial. Okay, a polynomial of order 5 will have 5 zeros. So, we can see that there will be, this means that there will be 5 zeros, 5 zeros. Okay. Now, the question that I would like you to answer is, are there any poles for this transfer function? Okay. There is no denominator, right, because we have just written down a finite length sequence, right, in terms of the Z transform. So, there is no zeros of the denominator, but the question is, are there values of Z for which the transfer function or the Z transform will go to infinity? The answer is yes, when Z is equal to 0, because we have 1 over Z. So, it will get 1 over 0, and so basically you will also find that there are 5 poles all occurring at Z equal to 0. Okay, there are 5 poles because there is a fifth order function, all of them will occur and they will occur at Z equal to 0. Okay, very important, when you look at a finite length sequence, the question is, will the Z transform exist? The condition for the Z transform is that the sequence must be bounded, and therefore, any finite length sequence we can safely say that the Z transform will exist. And the only possible poles that we can run into is at Z equal to 0. So, the region of convergence is the entire Z plane, possibly with the exclusion of Z equal to 0. So, the question that arises is the unit circle included in the region of convergence? Always yes, when it is a finite length sequence. So, therefore, just as we know that for a finite length sequence, the discrete time Fourier transform will exist if the individual values of the sequence x of n are bounded, then the discrete time Fourier transform will exist. So, in the same manner, we can say that the Z transform for a finite length sequence will always exist, except you have to be careful about Z equal to 0 and Z equal to infinity. Why Z equal to infinity? Just take a simple variation of this. Okay, same sequence, a simple variation of it. Okay, let's call this as x1 of n, and it has got a origin at the second point. Okay, so in this case, x1 of z is equal to, starting with z for the first term. Right? That's a z. Then you have plus 2, that's the coefficient with 0, exponent 0, then 5 times z inverse plus 7 times z minus 2, there is no z minus 3, and then you have a z minus 4. Okay? And now comes an important question. Again, it is a fifth order polynomial, there will be 5 zeros. What about poles? What about poles? Okay, z equal to 0 will be a pole, yes, because there are negative powers of z. Now, in this expression, you also have a positive power of z. So which means z equal to infinity is also a pole. So both poles are present, 0 and infinity will cause that function to go to infinity. Okay, but the region of convergence is anything between 0 and infinity. Okay. So which means that does the unit circle is it included? Of course it is included, and therefore any finite length sequence doesn't matter which way you shift it, the poles could change. It could be all the zeros are all the poles are at 0, or some poles are at 0, some are at infinity. However, the region of convergence will include the unit circle, and therefore finite length sequences will always have a well-defined region of convergence. They will also have a well-defined region of convergence which includes the unit circle, and therefore the discrete time Fourier transform will also exist, just as we know from the earlier study.